In this and the next few videos, we're going to be looking at applications of exponential functions. And exponential functions have a lot of applications because many phenomena follow a pattern of exponential growth or decay, and so they can be modeled by the exponential function f of x is equal to a times b to the power of x. And we'll see shortly why we've introduced this factor a. Let's take a look at an example, and population growth is a common example of exponential growth. If you have a culture of 8 bacteria, and are told that the number of bacteria doubles every hour, we could ask how many bacteria are there in 12 hours? Well, when time is equal to 0, you just have the original 8 bacteria. After an hour, you have the original 8 bacteria, but you've doubled it, so you've had to multiply the whole thing by 2. That would equal 16, but I'm going to leave it just as it is, as 8 times 2. After another hour, so after 2 hours, you have this amount, 8 times 2 bacteria, doubled again. So again, we multiply by 2. After 3 hours, we would take this amount that we had at the beginning of the hour and double it again. So now you have 8 times 2 times 2 times 2, 3 2's. If we use exponential notation for these, we could write this as 8 times 2 to the power of 3. This one would be 8 times 2 to the power of 2. This one would be 8 times 2 to the power of 1. And if you think about it, the original state could be written as 8 times 2 to the power of 0. So in each case, the form of our answer is the original amount, the initial amount, 8, multiplied by 2, which is the amount that it changes by each doubling period, raised to the number of doubling periods that there have been. So again, we've got the initial amount multiplied by the growth rate raised to the power of the number of growth periods. And if it's doubling every hour and there are 12 hours, that means we've got 12 growth periods. So instead of writing out the whole table, we could write that the amount is going to be equal to 8, our initial amount, doubled 12 times. So 8 times 2 to the power of 12. And plugging that into a calculator, we get that it's equal to 32,768 bacteria after 12 hours. So in general, we can work out exponential growth or decay problems using an equation like this. F of x is equal to a times b to the x. A, as we've seen, represents the initial amount. In our example, it was 8. B represents the growth or decay rate. In our example, it was 2 because every growth period the population was doubling. The number of growth or decay periods is given by the exponent. And that's important to recognize that the whole exponent represents the number of growth or decay periods. It's not necessarily the time, although it can be if you set up the equation that way, but the exponent is always the number of growth or decay periods. And the answer, the whole thing, the output, f of x, is the amount after x growth or decay periods. Let's look at another example. Now we've got the same culture of 8 bacteria, but now the number of bacteria doubles every 5 hours, not every hour. And we're asking how many bacteria are there in 12 hours. Well, if we want to know what's happening after 12 hours, but they've doubled every 5 hours, then the number of growth periods in that 12 hours is 12 hours divided by 5 hours per growth period. Now you could simplify that to 2.4 if you wanted to, but I'm going to leave it like that. And using the pattern that we had before, A is equal to 8, our initial amount, doubled 12 over 5 times, so 8 times 2 raised to the power of 12 over 5. Again, that's of the form f of x is equal to a times b to the power of x. And plugging that into a calculator, it's approximately equal to 42.2, which means that you've got 42 bacteria that are already fully there, and you've almost made the 43rd one. So again, you can use the exponential function to model population growth. The important thing to remember is that the exponent is always the number of growth periods. In the next video, we'll look at some more examples.